weeks for being too analytical and ineffectual. Laplace later sided with the Bourbons and was rewarded with the return of his original title of Marquis when the monarchy was restored. Laplace's demon was a side note to a career that also encompassed physics and astronomy, where Laplace was the first to postulate the concept of a black hole. His many contributions to mathematics were in classical mechanics, probability theory, and algebraic transformations. Laplace died in Paris in 1827. Key works: 1798, 1828 Celestial Mechanics, 1812 Analytic Theory of Probability, 1814 A Philosophical Essay on Probabilities. See also Probability Calculus, Newton's Laws of Motion, the Butterfly Effect. In context. Key figure: Simeon Poisson field probability before 1662 English merchant John Grant publishes natural and political observations upon the bills of mortality, marking the birth of statistics. 1711 Abraham de Moivre's De Mensura Sortis describes what is later known as the Poisson distribution. After 1898 Russian statistician Ladislaus Bortkiewicz uses the Poisson distribution to study the number of Prussian soldiers killed by horse kicks. 1946 British statistician R.D. Clarke publishes a study, based on the Poisson distribution, of patterns of V1 and V2 flying bomb impacts on London. In statistics, the Poisson distribution is used to model the number of times a randomly occurring event happens in a given interval of time or space. Introduced in 1837 by French mathematician Simeon Poisson, and based on the work of Abraham de Moivre, it can help to forecast a wide range of possibilities. Take, for example, a chef who needs to forecast the number of baked potatoes that will be ordered in her cafe. She needs to decide how many potatoes to pre-cook each day. She knows the daily average order, and decides to prepare N potatoes where there is at least 90% certainty that N will match demand. To use the Poisson distribution to calculate N, conditions must be met, orders must occur randomly, singly, and uniformly. On average, the same number of potatoes are ordered each day. If these conditions apply, the chef can find the value of N, how many potatoes to pre-bake. The average number of events per unit of space or time is key. If lambda equals 4, and the number of potato orders on any one day is b, the probability that b is less than or equal to 6 is 89%, while the probability that b is less than or equal to 7 is 95%. The chef must be at least 90% sure that demand will be met, so N will be 7 here. Simeon Poisson is credited with finding the Poisson distribution, but this may be an example of Stigler's law. No scientific discovery is credited to the true discoverer. See also, Probability Euler's number normal distribution, the birth of modern statistics. In context. Key figure: Friedrich Wilhelm Bessel field. Applied geometry before 1609 Johannes Kepler shows that the orbits of the planets are ellipses. 1732 Daniel Bernoulli uses what later become known as Bessel functions to study the vibrations of a swinging chain. 1764 Leonhard Euler analyzes a vibrating membrane using what are later understood to be Bessel functions. After 1922 British mathematician George Watson writes his hugely influential A treatise on the theory of Bessel functions. In the early 1800s, German mathematician and astronomer Friedrich Wilhelm Bessel gave solutions to a particular differential equation, the so-called Bessel equation. He systematically investigated these functions in 1824. Now known as Bessel functions, they are useful to scientists and engineers. Central to the analysis of waves, such as electromagnetic waves moving along wires, they are also used to describe the diffraction of light, the flow of electricity or heat in a solid cylinder, and the motions of fluids. Movement of the planets. The origins of Bessel functions lie in the pioneering work of German mathematician and astronomer Johannes Kepler in the early 1600s on the motions of the planets. His meticulous analysis of observations led him to realize that the orbits of the planets around the Sun are elliptical, not circular, and he described the three key laws of planetary motion. Mathematicians later used Bessel functions to make breakthroughs in various fields. Daniel Bernoulli found equations for the oscillations of a pendulum, and Leonhard Euler developed corresponding equations for the vibration of a stretched membrane. Euler and others also used Bessel functions to find solutions to the three-body problem, concerned with the motion of a body, such as a planet or moon, being acted upon by the gravitational fields of two other bodies. Bessel's functions are very beautiful functions, in spite of their having practical applications. E. W. Hobson, British mathematician. See also, the problem of maxima calculus, the law of large numbers, Euler's number Fourier analysis. In context. Key figures. Charles Babbage, Ada Lovelace Field. Computer science before. 1617 Scottish mathematician John Napier invents a manual calculating device. 1642-44 in France, Blaise Pascal creates a calculating machine. 1801 French weaver Joseph-Marie Jacquard demonstrates the first programmable machine. A loom controlled by a punch card. After 1944 British codebreaker Max Newman builds Colossus, the first digital electronic programmable computer. British mathematician and inventor Charles Babbage anticipated the computer age by more than a century with two ideas for mechanical calculators and thinking machines. The first he called the difference engine, a calculating machine that would work automatically, using a combination of brass cogs and rods. Babbage only managed to part-build the machine, but even this was able to process complex calculations accurately in moments. The second, more ambitious, idea was the analytical engine. It was never built, but was envisaged as a machine that could respond to new problems and solve them without human intervention. The project received crucial input from Ada Lovelace, a brilliant young mathematician. Lovelace anticipated many of the key mathematical aspects of computer programming and foresaw how the machine could be used to analyze any kinds of symbol. Charles Babbage was spurred to start his work on a mechanical calculator by the errors he found in astronomical tables produced by poorly paid and unreliable workers. Automatic calculation. In the 17th and 18th centuries, mathematicians such as Gottfried Leibniz and Blaise Pascal had created mechanical calculating aids, but these were limited in power and also prone to error as human input was needed at every step. Babbage's idea was to create a calculating machine that worked automatically, eliminating human error. He called his machine the difference engine because it allowed complex multiplications and divisions to be reduced to additions and subtractions, differences, that could be handled by scores of interlocking cogs. It would even print out the results. No previous calculator had ever worked with numbers larger than 4 digits. Yet the difference engine was designed to handle numbers of up to 50 digits by means of more than 25,000 moving parts. To set up the machine for a calculation, each number was represented by a column of cogwheels, and each cogwheel was marked with digits from 0 to 9. A number was set by turning the cogwheels in the column to show the correct digit on each. The machine would then work through the entire calculation automatically. Babbage built several small working models with just 7 number columns, but remarkable calculating power. In 1823, he managed to persuade the British government to part-fund the project, with the promise that it would make producing official tables much quicker, cheaper, and more accurate. However, the full machine was hugely expensive to develop, and tested the technological capability of the day to its limits. After 2 decades' work, the government cancelled the project in 1842. Meanwhile, in drawings and calculations, Babbage had also been working on his idea for an analytical engine. His papers suggest that the machine, if built, could have been close to what we now call a computer. His design anticipated virtually all of the key components of the modern computer, including the central processing unit, memory storage, and integrated programs. One problem facing Babbage was what to do with numbers carried over into the next column when adding up columns of digits. At first, he used a separate mechanism for each carryover, but that proved too complicated. Then he split his machine into two parts, the mill and the store, which made it possible to separate the addition and carryover processes. The mill was where the arithmetical operations were performed. The store was where numbers were held before processing and then received back from the mill after processing. The mill was Babbage's version of a computer's CPU, while the store acted as its memory. The idea of telling a machine what it should do, programming, came from a French weaver, Joseph-Marie Jacquard. He developed a loom that used cards punched with holes to tell it how to weave complex patterns in silk. In 1836, Babbage realized he too could use punched cards to control his own machine but also to record results and calculation sequences. At each increase of knowledge, as well as on the contrivance of every new tool, human labor becomes abridged. Charles Babbage. This replica of the demonstration model Babbage made in 1832 of difference engine number 1 has 3 columns, each with its numbered cogwheels. 2 are for calculation, 1 for the result. A supporting genius. One of the greatest advocates for Babbage's work was his fellow mathematician Ada Lovelace, who wrote of the analytical engine that it would weave algebraic patterns just as the Jacquard loom weaves flowers and leaves. As a teenager in 1832, Lovelace had seen one of the difference engine models working and had been instantly entranced. In 1843, she arranged the publication of her translation of a pamphlet about the analytical engine written by Italian engineer Luigi Minabrea, to which she added extensive explanatory notes. Many of these notes covered systems that would become part of modern computing. In Note G, Lovelace described possibly the first computer algorithm. To show an implicit function can be worked out by the engine without human head and hands first. She also theorized that the engine could solve problems by repeating a series of instructions, a process known today as looping. Lovelace envisaged a program card, or set of cards, that returned repeatedly to its original position to work on the next data card or set. In this way, Lovelace argued, the machine could solve a system of linear equations or generate extensive tables of prime numbers. Perhaps the greatest insight in her notes was Lovelace's vision of machines as mechanical brains with wide applications. The engine can arrange and combine its numerical quantities exactly as if they were letters or any other general symbols. She wrote, realizing that any kind of symbol, not just numbers, could be manipulated and processed by machines. This is the difference between calculation and computation, and the basis of the modern computer. Lovelace also foresaw how such machines would be limited by the quality of the input. Arguably, the first programmable computer, rather than calculator, was created by Konrad Zuse in 1938. The object of the analytical engine is twofold. First, the complete manipulation of number. Second, the complete manipulation of algebraical symbols. Charles Babbage. Delayed legacy. Lovelace's plans to develop Babbage's work were curtailed by her early death, by which time Babbage himself was tired, ill, and disillusioned by the lack of support for his difference engine. The high-precision mechanics required to build the machine were beyond what any engineer could achieve at the time. Largely forgotten until they were republished in 1953, Lovelace's notes confirm that she and Babbage foresaw many of the features of the computer now found in every home and office. The more I study, the more insatiable I feel my genius for it to be. Ada Lovelace. Ada Lovelace. Born Augusta Byron in London in 1815, Ada, Countess of Lovelace, was the only legitimate child of the poet Lord Byron. Byron left England a few months after her birth, and Lovelace never saw her father again. Her mother, Lady Byron, was mathematically gifted. Byron called her his Princess of Parallelograms, and insisted Lovelace study mathematics too. Lovelace became renowned for her talents in mathematics and languages. She met Charles Babbage when she was 17 and was fascinated by his work. 2 years later, she married William King, Earl of Lovelace, with whom she had 3 children, but she continued to study mathematics and follow the progress of Babbage, who called her the Enchantress of Number. Lovelace wrote exhaustive notes on Babbage's analytical engine. She set out many ideas about what was to become computing, earning herself a reputation as the first computer programmer. Lovelace died in 1852 of uterine cancer. In line with her wishes, she was buried next to her father. See also, binary numbers matrices, the infinite monkey theorem, the Turing machine. Information theory, the four-color theorem. In context. Key figure: Carl Gustav Jacob Jacobi Fields. Number theory, geometry before 1655. John Wallis applies calculus to the length of an elliptic curve. The elliptic integral he derives is defined by an infinite series of terms. 1799. Carl Gauss determines the key characteristics of elliptic functions, but his work is not published until 1841. 1827. 28. Niels Abel independently derives and publishes the same findings as Gauss. After 1862, German mathematician Karl Weierstrass develops a general theory of elliptic functions, showing that they can be applied to problems in both algebra and geometry. The squash circle of an ellipse is one of the most recognizable curves in math. Ellipses have a long history in mathematics. They were studied by the ancient Greeks as one of the conic sections. Slicing through a cone horizontally creates a circle. Slicing at a steeper angle creates an ellipse. An ellipse is a closed curve that is defined as the set of all points in a plane, the sum of whose distances from 2 fixed points, each one called a focus, is always the same number. In 1609, German astronomer and mathematician Johannes Kepler demonstrated that the orbits of the planets were elliptical, with the Sun being located at one of the foci. I learnt with as much astonishment as satisfaction that 2 young geometers succeeded in their own individual work in considerably improving the theory of elliptic functions. Adrien Marie Legendre. New tools. Just as the mathematics of a circle could be used to model and predict natural phenomena that varied and repeated in a rhythmic way, such as the up and down motion of a simple sound wave, the mathematics of the ellipse can be used to do the same for phenomena that follow more complex periodic patterns, such as electromagnetic fields or the orbital motion of planets. The genesis of such tools, the elliptic functions, began in England with 17th-century mathematicians John Wallis and Isaac Newton. Working independently, they developed a method for calculating the arc length, or length of a section, of any ellipse. With later contributions, their technique was developed into the elliptic functions and became a way of analyzing many kinds of complex curves and oscillating systems beyond the simple ellipse. Practical applications. In 1828, Norwegian Niels Abel and German Carl Jacobi, again working independently, showed wider applications for elliptic functions in both mathematics and physics. For example, these functions appear in the 1995 proof of Fermat's last theorem, and the latest public key cryptography systems. Since Abel died at 26, just months after making his major discoveries, many of these applications were developed by Jacobi. Jacobi's elliptic functions are complex, but a more simple form, the p-function, was introduced in 1862 by German mathematician Karl Weierstrass. P-functions are used in classical and quantum mechanics. Elliptic functions are used to define the trajectories of spacecraft such as the Dawn probe, which explored the dwarf planet Ceres and the asteroid Vesta in the asteroid belt. Carl Gustav Jacob Jacobi. Born in Potsdam, Prussia, in 1804, Carl Gustav Jacob Jacobi was initially tutored by an uncle. Having learned all that school could teach him by the age of 12, he had to wait until he was 16 to be allowed to attend Berlin University, and spent the intervening years teaching himself mathematics. He continued to do so when he found the university courses too basic. He graduated within a year, and in 1832 he became a professor at the University of Königsberg. Falling ill in 1843, Jacobi returned to Berlin, where he was supported by a pension from the King of Prussia. In 1848, he ran unsuccessfully for Parliament as a Liberal candidate, and the offended king temporarily withdrew his support. In 1851, aged just 46, Jacobi contracted smallpox and died. Key work: 1829 Fundamenta Nova Theoria Functionum Ellipticarum. See also Huygens' Tautochrone curve calculus, Newton's laws of motion, cryptography proving Fermat's last theorem. In context. Key figure: János Bolyai field geometry before 1733 in Italy, mathematician Giovanni Sacchari fails to prove Euclid's parallel postulate from his other four postulates. 1827 Carl Friedrich Gauss publishes his Disquisitions Generales circa superficies curvas, defining the intrinsic curvature of a space, which can be deduced from within the space. After 1854 Bernhard Riemann describes the kind of surface that has hyperbolic geometry. 1915 Einstein describes gravity as curvature in spacetime in his general theory of relativity. The parallel postulate is the fifth of 5 postulates from which Euclid deduced his theorems of geometry in his Elements. The PP was controversial among the ancient Greeks, since it did not seem as self-evident as Euclid's other postulates, nor was there an obvious way of verifying it. However, without the PP, many elementary theorems in geometry could not be proved. Over the next 2,000 years, mathematicians would stake their reputations on attempts to resolve the issue. In the 5th century CE, the philosopher Proclus argued that the PP was a theorem that could be derived from the other postulates, and should therefore be struck out. During the Golden Age of Islam, mathematicians attempted to prove the PP. Persian polymath Nasir al-Din al-Tusi showed that the PP is equivalent to stating that the sum of angles in any triangle is 180 degrees, but the PP nonetheless remained controversial. In the 1600s, new translations of Elements reached Europe, and Giovanni Sacchari showed that if the PP was untrue, then the sum of angles in a triangle was always either less than or greater than 180 degrees. By the early 1800s, Hungarian János Bolyai and Russian Nikolai Lobachevsky independently proved the validity of a hyperbolic, non-Euclidean geometry in which the PP did not hold but the other 4 of Euclid's postulates did. Bolyai claimed to have created another world out of nothing, but the idea was not well received in its time. Gauss acknowledged its validity, but claimed to have discovered it first. Gauss's idea of the intrinsic curvature of a surface or space was an important tool in establishing this new world, but he left little evidence of having developed non-Euclidean geometry himself. He did, however, consider that the universe might be non-Euclidean. Subsequent advances by Bernhard Riemann, Eugenio Beltrami, Felix Klein, David Hilbert, and others mean that today, non-Euclidean geometries are no longer seen as exotic, and physicists have given serious consideration to whether our universe is indeed flat or curved. Leave the science of parallels alone. I was ready to remove the flaw from geometry, turned back when I saw that no man can reach the bottom of this night. Wolfgang Bolyai, father of János Bolyai. Artistic explorations. Hyperbolic geometry also features in art. Models devised by Henri Poincaré inspired many graphic works by M. C. Escher, while some mathematicians, notably Dana Taimina, have used art and craft techniques to make these new worlds intuitively graspable. Crochet models of hyperbolic surfaces created by Dana Taimina are more tactile than paper models. She claims that the crocheting process helps develop geometrical intuition. Dana Taimina. Born in Latvia in 1954, Dana Taimina began her career in the fields of computer science and the history of mathematics. After teaching for 20 years at the University of Latvia, she moved to Cornell University in the United States in 1996, where a chance encounter opened up a new area of interest. Taimina attended a geometry workshop led by David Henderson in which he demonstrated how to make a paper model of a hyperbolic surface. Henderson himself had learned the technique from pioneering American topologist William Thurston. Taimina went on to make her own models of hyperbolic surfaces using crochet to assist in her teaching. The models were a success, breaking the stereotype of mathematics as a field unrelated to arts and crafts. Taimina has since embarked on a second career as a mathematician-artist. Key work: 2004 Experiencing Geometry with David W. Henderson. See also, Euclid's Elements Projective Geometry Topology 23 Problems for the 20th Century Minkowski Space. In context. Key figure: Évariste Galois Fields. Algebra, number theory before. 1799 Italian mathematician Paolo Ruffini considers the sets of permutations of roots as an abstract structure. 1815 Augustin Louis Cauchy, a French mathematician, develops his theory of permutation groups. After 1846 Galois work is published posthumously by fellow Frenchman Joseph Leville. 1854 British mathematician Arthur Cayley extends the work of Galois to a full theory of abstract groups. 1872 German mathematician Felix Klein defines geometry in terms of group theory. Group theory is a branch of algebra that pervades modern mathematics. Its genesis was largely due to French mathematician Évariste Galois, who developed it in order to understand why only some polynomial equations could be solved algebraically. In so doing, he not only gave a definitive answer to a historical quest that had begun in ancient Babylon, but also laid the foundations of abstract algebra. Galois' approach to this problem was to relate it to a question in another area of mathematics. This can be a powerful strategy when the other area is well understood. In this case, however, Galois first had to develop the theory of the simpler area, the theory of groups, in order to tackle the more difficult problem. The link he made between the two areas is now called Galois theory. Arithmetic of symmetries. A group is an abstract object. It consists of a set of elements and an operation that combines them, subject to some axioms. When these elements include shapes, groups can be thought of as encoding symmetry. Simple symmetries, such as those of a regular polygon, are intuitively graspable. For example, an equilateral triangle with the vertices A, B, and C can be rotated in 3 ways around its center, and be reflected in 3 different lines. Each of these 6 transformations fits the triangle onto itself. It looks exactly the same, except that the vertices are permuted. A clockwise rotation of 120 degrees sends vertex A to where B was, B to C, and C to A, while a reflection in the vertical line through A swaps vertices B and C. The 3 rotations and the reflections give all possible symmetries of the triangle ABC. One way to see the symmetries of the triangle is to consider all of the possible permutations of the vertices. A rotation or reflection can send the vertex A to one of 3 points. From each of these possibilities, the vertex B has 2 available destinations. The destination of the third vertex is now determined because the triangle is rigid, so there are 2 is equal to 6 possibilities. The symmetry groups of polygons can be thought of as permutations of a set of elements. The symmetry group of the equilateral triangle is a member of a small group called D. Évariste Galois. Born in 1811, Évariste Galois lived a brief but fiery and brilliant life. He was already familiar as a teenager with the works of Lagrange, Gauss, and Cauchy, but failed to enter the prestigious École Polytechnique, possibly due to his mathematical and political impetuousness, though no doubt affected by the suicide of his father. In 1829, Galois enrolled at the École Préparatoire, only to be expelled in 1830 for his politics. A staunch Republican, he was arrested in 1831 and imprisoned for 8 months. Shortly after his release in 1832, he became involved in a duel. It is unclear whether this was over a love affair or politics. Badly wounded, he died the next day, leaving behind just a handful of mathematical papers which contain the foundations of group theory, finite field theory, and what is now called Galois theory. Key works: 1830 Sur la théorie de nombres 1831 Premier Memoir. The equilateral triangle has 6 symmetries. They are rotation through 120 degrees, 240 degrees, and 360 degrees, and reflection through a vertical line through A, B, or C. The diagram above shows the results of applying one symmetry after another to E, the identity element, and how they are written. Rho sigma means rotate through 120 degrees twice and reflect. Axioms of group theory. Group theory has 4 main axioms. The first is the identity axiom. It states that a unique element exists that does not change any element in the group when combined with it. With the ABC triangle, the identity is the rotation of 0 degrees. The second axiom is the inverse axiom. It says that every element has a unique inverse element. Combining the two yields the identity element. The third axiom concerns associativity, which means that the result of operations on elements does not depend on the order in which they are applied. For example, if you combine any set of 3 elements with a multiplication operator, you can perform the operations in any order. So if the elements 1, 2, and 3 are members of a group, then 3 is equal to 2, 3 is equal to 6, and 1 is equal to 1, 6 is equal to 6, all giving the same result. The fourth axiom is closure, meaning that a group should have no elements outside the group as a result of performing the operations. One example of a group obeying all 4 axioms is the set of integers with the operation of addition. The unique identity element is 0, and the inverse of any integer n is n, as n plus n equals 0 equals n plus n. The addition of integers is associative, and the set is also closed, because adding any of the integers together gives another integer. Groups can also have a further attribute known as commutativity. If a group is commutative, it is known as an abelian group. This means that its elements can be swapped around without changing the result. Integers added in any order will give the same result, so the set of integers with the operation of addition is an abelian group. The possible rotations of a Rubik's cube form a mathematical group with 43,252,3,274,489,856,000 elements, but solving the cube from any position requires no more than 26 turns of 90 degrees. Wherever groups disclose themselves, or could be introduced, simplicity crystallized out of comparative chaos. Eric Temple Bell, Scottish mathematician. Galois groups and fields. Groups are just one kind of abstract algebraic structure among many. Closely related structures include rings and fields, which are also defined in terms of a set with operations and axioms. A field contains 2 operations. Complex numbers are a field. The field of complex numbers is the territory in which solutions to polynomial equations are found. Galois theory relates the solvability of a polynomial equation to a group, specifically, to the permutation group that encodes possible rearrangements of its roots. Galois showed that this group, now called a Galois group, must have one kind of structure if the equation is algebraically solvable, and a different kind of structure if it is not. Galois groups of quartic equations and simpler polynomials are solvable, but those of higher degree polynomials are not. Modern algebra is an abstract study of groups, rings, fields, and other algebraic structures. Group theory continues to develop in its own right, and has many applications. Group theory is used to study symmetries in chemistry and physics, for example, and can be used in public key cryptography, which secures much of today's digital communication. We need a supermathematics in which the operations are as unknown as the quantities they operate on. Such a supermathematics is the theory of groups. Arthur Eddington, British astrophysicist. Group theory in physics. The universe, as we understand it through physics, is full of symmetries, and group theory is proving a powerful tool for both understanding and prediction. Physicists use the Lie groups, named after the 19th century Norwegian mathematician Sophus Lie. Lie groups are continuous, not discrete. For example, They model the infinite number of rotational symmetries, such as those associated with a circle, rather than the finite number of transformations of a polygon. In 1915, German algebraist Emmy Noether demonstrated how Lie groups related to conservation laws. By the 1960s, physicists began to use group theory to classify subatomic particles. But the mathematical groups they used included a combination of symmetries that no known particles had. Scientists tried looking for a particle with that combination of symmetries, and found the omega- particle. More recently, the Higgs boson has filled another such gap. See also, the algebraic resolution of equations Emmy Noether and abstract algebra finite simple groups. The ATLAS detector at the CERN accelerator is designed to study subatomic particles, including those predicted by group theory. In context. Key figure: William Rowan Hamilton Field. Number systems before 1572. Italy's Raphael Bombelli creates complex numbers by combining real numbers, based on the unit 1, with imaginary numbers, based on the unit I. 1806. Jean Robert Argand creates a geometrical interpretation of complex numbers by plotting them as coordinates to create the complex plane. After 1888. Charles Hinton invents the tesseract, which is an extension of the cube into 4 spatial dimensions. A tesseract has 4 cubes, 6 squares, and 4 edges meeting at every corner. An extension of complex numbers, quaternions are used to model, control, and describe motion in 3 dimensions, which is essential in, for example, creating the graphics of a video game, planning a space probe's trajectory, and calculating the direction in which a smartphone is pointing. Quaternions were the brainchild of William Rowan Hamilton, an Irish mathematician who was interested in how to model movement mathematically in 3-dimensional space. In 1843, in a flash of inspiration, he realized that the third-dimension problem could not be solved with a 3-dimensional number, but needed a 4-dimensional one. Movements and rotations. Complex numbers are 2-dimensional. They are made up of a real and an imaginary part, for example, 1 plus 2i. As a result, the 2 parts of any complex number can act as coordinates, and the number can be plotted on a surface or plane. The 2-dimensional complex plane extends the 1-dimensional number line by combining real numbers with imaginary units. The plotting of complex numbers then enables the calculation of motion and rotation in 2 dimensions. Any linear motion from point A to B can be expressed as the addition of 2 complex numbers. Adding more numbers creates a sequence of movements across the plane. To describe rotation, complex numbers are multiplied together. Every multiplication by I, the imaginary unit, results in a 90 degrees rotation, and a rotation of any other angle is due to some factor or fraction of I. Once complex numbers were understood, the next challenge for mathematicians was to create a number that worked the same way in a 3-dimensional space. The logical answer was to add a third number line, j, which ran at 90 degrees to both the real and imaginary number lines, but no one could figure out how such a number added, multiplied, and so on. Since quaternions can model and control the motion of objects in 3 dimensions, they are particularly useful in virtual reality games. 4 dimensions. Hamilton's solution was to add a 4th non-real unit, k. This created a quaternion, with a basic structure of a plus by plus cj plus dk, where a, b, c, and d are real numbers. The 2 additional quaternion units, j and k, share similar properties to I and are imaginary. A quaternion can define a vector, or a line in 3-dimensional space, and can describe an angle and direction of rotation around that vector. Like the complex plane, simple quaternion mathematics, combined with basic trigonometry, offers a way to describe all kinds of movements within 3-dimensional space. An undercurrent of thought was going on in my mind which gave at last a result. An electric circuit seemed to close, and a spark flashed forth, the herald of many long years. William Rowan Hamilton. William Rowan Hamilton. Born in Dublin in 1805, Hamilton became interested in mathematics from the age of 8 after meeting Zira Colburn, a touring American mathematical child prodigy. At the age of 22, while still studying at Trinity College, Dublin, he was appointed both Professor of Astronomy at the University and Royal Astronomer of Ireland. Hamilton's expertise in Newtonian mechanics enabled him to calculate the paths of heavenly bodies. He later updated Newtonian mechanics into a system that enabled further advances to be made in electromagnetism and quantum mechanics. In 1856, he tried to capitalize on his skills by launching the Icosian game, in which players search for a path connecting the points of a dodecahedron without returning to the same point twice. Hamilton sold the rights to the game for £25. He died in 1865, following a severe attack of gout. Key works: 1853 Lectures on Quaternions, 1866 Elements of Quaternions. See also, Imaginary and complex numbers, coordinates, Newton's laws of motion, the complex plane. In context. Key figure: Eugene Catalan, field number theory before. Circa 1320, French philosopher and mathematician Levi Ben Gershon shows that the only powers of 2 and 3 that differ by 1 are 8 is equal to 2 and 9 is equal to 3. 1738, Leonhard Euler proves that 8 and 9 are the only consecutive square or cube numbers. After 1976, Dutch number theorist Robert Tiedemann proves that, if more consecutive powers exist, there are only a finite number of them. 2002, Pret-a-Mihalescu proves Catalan's conjecture, 158 years after it was formulated in 1844. Many problems in number theory are easy to pose, but extremely difficult to prove. Fermat's last theorem, for example, remained a conjecture for 357 years. Like Fermat's conjecture, Catalan's conjecture is a deceptively simple claim about powers of positive integers that was proved long after its initial statement. In 1844, Eugene Catalan claimed that there is only one solution to the equation xy equals 1, where x, y, m, and n are natural numbers and m and n are greater than 1. The solution is x equals 3, m equals 2, y equals 2, and n equals 3, since 3 minus 2 is equal to 1. In other words, squares, cubes, and higher powers of natural numbers are almost never consecutive. 500 years before, Gersonides had proved a special case of the claim. He used only powers of 2 and 3. Solving the equations 3-2 is equal to 1 and 2-3 is equal to 1. In 1738, Leonhard Euler similarly proved a case in which the only powers allowed were squares and cubes. Euler did this by solving the equation xy equals 1. This was closer to Catalan's conjecture, but did not allow for the possibility that larger powers or exponents could result in consecutive numbers. Becoming a theorem. Catalan himself said that he could not prove his conjecture completely. Other mathematicians tackled the problem, but it was only in 2002 that Romanian mathematician Pret-a-Mihalescu solved the outstanding issues and turned conjecture into theorem. It might seem that Catalan's conjecture must be false, since simple calculations quickly yield examples of powers that are almost consecutive. For example, 3 minus 5 is equal to 2, and 2 minus 5 is equal to 3. On the other hand, even these near solutions are rare. One approach to proving the conjecture appeared to involve making many calculations. In 1976, Robert Tiedemann found an upper bound for x, y, m, and n. This proved that there is only a finite number of powers that can be consecutive. The truth of Catalan's conjecture could now be tested by checking each of these powers. Unfortunately, Tiedemann's upper bound is astronomically large, making such computation practically unfeasible even for modern computers. Mihalescu's proof of Catalan's conjecture does not involve any such computation. Mihalescu built on 20th century advances that had proved m and n must be odd primes for any further solutions of xy equals 1. His proof is not as formidable as Andrew Wiles's proof of Fermat's last theorem, but it is still highly technical. If squared and cube numbers are lined up in order of their values, the difference between each value becomes clear. The difference between 2 and 3 is 1, and Catalan's conjecture states that this is the only pair of squares, cubes, or higher powers that differ by 1. Eugene Catalan. Born in Bruges, Belgium, in 1814, Eugene Catalan studied under French mathematician Joseph Leville at the École Polytechnique in Paris. Catalan was a Republican from an early age and a participant in the 1848 Revolution. His political beliefs led to his expulsion from a number of academic posts. Catalan was particularly interested in geometry and combinatorics, and his name is associated with the Catalan numbers. This sequence counts, among other things, the ways that polygons can be divided into triangles. Although he considered himself French, Catalan won recognition in Belgium, where he lived from his appointment as professor of analysis at the University of Liège in 1865 until his death in 1894. Key works: 1860 Trait élémentaire de séries, 1890 Intégrales eulériennes aux elliptiques. See also Pythagoras Diophantine equations, the Goldbach conjecture, taxicab numbers proving Fermat's last theorem. In context. Key figure: James Joseph Sylvester Fields. Algebra, number theory before 200 BC. The ancient Chinese text The 9 Chapters on the Mathematical Art presents a method for solving equations using matrices. 1545 Gerolamo Cardano publishes techniques using determinants. 1801 Carl Friedrich Gauss uses a matrix of 6 simultaneous equations to compute the orbit of the asteroid Pallas. After 1858 Arthur Cayley formally defines matrix algebra, and proves results for 2-2 and 3-3 matrices. Matrices are rectangular arrays of elements, arranged in rows and columns enclosed by square brackets. The rows and columns can be extended indefinitely, which enables matrices to store vast amounts of data in an elegant and compact manner. Although a matrix contains many elements, it is treated like one unit. Matrices have applications in mathematics, physics, and computer science, such as in computer graphics and describing the flow of a fluid. The earliest known evidence for such arrays comes from the ancient Mayan civilization of Central America, circa 2600 BC. Some historians believe the Maya people manipulated numbers in rows and columns to solve equations, and cite grid-like decorations on their monuments and priestly robes as evidence. Others, however, doubt these patterns represent actual matrices. The first verified instance of the use of matrices comes from ancient China. In the 2nd century BC, the textbook The 9 Chapters on the Mathematical Art described how to set out a counting board and use a matrix-like method to solve linear simultaneous equations with several unknown values. This method was similar to the elimination system introduced by German mathematician Carl Gauss in the 1800s, which is still used today for solving simultaneous equations. The dimensions of a matrix are important, as operations such as addition and subtraction require the matrices involved to have the same dimensions. The 2-2 matrices below are square matrices, meaning that they have the same number of rows as they have columns. The graphic below shows how matrices are added together by adding the elements in corresponding positions. Matrix arithmetic. In 1850, British mathematician James Joseph Sylvester first used the term matrix to describe an array of numbers. Shortly after Sylvester introduced the term, his friend and colleague Arthur Cayley formalized the rules for manipulating matrices. Cayley showed that the rules of matrix algebra are different from those in standard algebra. 2 matrices of the same size are added by simply adding corresponding elements. Matrices with different dimensions cannot be added. Matrix multiplication is, however, quite different from multiplication of numbers. Not all matrices can be multiplied together. In matrix multiplication, AB can only be calculated if the row count of B is the same as the column count of A. Matrix multiplication is noncommutative, meaning that even where both A and B are square matrices, AB is not equal to BA. The arrays found in Mayan relics suggest to some historians that the Maya used matrices to solve linear equations. However, others believe they were merely replicating patterns in nature, such as on a turtle's shell. Square matrices. Because of their symmetry, square matrices have particular properties. For example, a square matrix can be repeatedly multiplied by itself. A square matrix of size n with the value 1 along the diagonal starting top left, and the value 0 everywhere else, is called the identity matrix. Every square matrix has an associated value called its determinant, which encodes many of the matrix's properties and can be computed by arithmetic operations on the matrix's elements. Square matrices whose elements are complex numbers, and whose determinants are not zero, form an algebraic structure called a group. Theorems that are true for groups are therefore also true for such matrices, and advances in group theory can be applied to matrices. Groups can also be represented as matrices, enabling difficult problems in group theory to be expressed in terms of matrix algebra, which is more easily solved. Representation theory, as this field is known, is applied in number theory and analysis, and in physics. Multiplying two matrices together is achieved by multiplying the horizontals in the first matrix by the vertical numbers in the second and adding the results. In matrix algebra, switching around the order in which the two matrices are multiplied produces a different result as shown here with the multiplication of two square matrices. Determinants. The determinant of a matrix was named by Gauss, due to the fact that it determines whether the system of equations represented by the matrix has a solution. As long as the determinant is not zero, the system will have a unique solution. If the determinant is zero, the system may have either no solution or many. In the 1600s, Japanese mathematician Seiki Takakazi had shown how to calculate the determinants of matrices up to size 5. Over the following century, mathematicians uncovered the rules for finding determinants of larger and larger arrays. In 1750, Swiss mathematician Gabriel Cramer stated a general rule for the determinant of a matrix with m rows and n columns, but he failed to give the proof of this rule. In 1812, French mathematicians Augustin-Louis Cauchy and Jacques Binet proved that when two square matrices of the same size are multiplied, the determinant of this product is, in fact, the same as the product of their individual determinants, det AB equals. This rule simplified the process of finding the determinant of a very large matrix by breaking it down into the determinants of two smaller matrices. A linear transformation in two dimensions maps lines through the origin to other lines through the origin, and parallel lines to parallel lines. Linear transformations include rotations, reflections, enlargements, stretches, and shears. The image of any point is found by multiplying the matrix by the column vector representing the point. In the examples above, the original shape is the pink square, with vertices, and the image is the green quadrilateral. Transformation matrices. Matrices can be used to represent linear geometric transformations such as reflections, rotations, translations, and scalings. Transformations in two dimensions are encoded by two matrices, while 3D transformations involve 3 matrices. The determinant of a transformation matrix contains information about the area or volume of the transformed figure. Today, computer-aided design software makes extensive use of matrices for this purpose. Modern applications. Matrices can store vast amounts of data compactly, making them essential across math, physics, and computing. Graph theory uses matrices to encode how a set of vertices is connected by edges. One formulation of quantum physics, called matrix mechanics, makes extensive use of matrix algebra, and particle physicists and cosmologists use transformation matrices and group theory to study the symmetries of the universe. Matrices are used to represent electrical circuits for solving problems about voltage and current. They are also important in computer science and cryptography. Stochastic matrices, whose elements represent probabilities, are used by search engine algorithms for ranking web pages. Programmers use matrices as keys when encrypting messages. Letters are assigned individual numerical values, which are then multiplied by the numbers in the matrix. The larger the matrix used, the more secure the encryption is. I have not thought it necessary to undertake the labor of a formal proof of the theorem in the general case of a matrix of any degree. Arthur Cayley. James Joseph Sylvester. Born in 1814, James Joseph Sylvester began his studies at University College London, but left when he was accused by another student of wielding a knife. He then went to Cambridge and came second in the university examinations, but was not allowed to graduate because, as a Jew, he would not swear allegiance to the Church of England. Sylvester taught briefly in the U.S., but faced similar difficulties there. Returning to London, he studied law and was admitted to the bar in 1850. He also began to work on matrices with fellow British mathematician Arthur Cayley. In 1876, Sylvester returned to the U.S. as a math professor at Johns Hopkins University, Maryland, where he founded the American Journal of Mathematics. Sylvester died in London in 1897. Key works: 1850 on a new class of theorems, 1852 on the principle of the calculus of forms, 1876 treatise on elliptic functions. See also, algebra coordinates, probability graph theory, group theory, cryptography. In context. Key figure: George Boole, Field Logic before 350 BC. Aristotle's philosophy discusses syllogisms. 1697 Gottfried Leibniz tries, unsuccessfully, to use algebra to formalize logic. After 1881 John Venn introduces Venn diagrams to explain Boolean logic. 1893 Charles Sanders Peirce uses truth tables to show outcomes of Boolean algebra. 1937 Claude Shannon uses Boolean logic as the basis for computer design in his A Symbolic Analysis of Relay and Switching Circuits. Mathematics had never more than a secondary interest for him, and even logic he cared for chiefly as a means of clearing the ground. Mary Everest Boole, British mathematician and wife of George Boole. Logic is the bedrock of mathematics. It provides us with the rules of reasoning and gives us a basis for deciding on the validity of an argument or proposition. A mathematical argument uses the rules of logic to ensure that if a basic proposition is true, then any and all statements constructed from that proposition will also be true. The earliest attempt to set out the principles of logic was carried out by the Greek philosopher Aristotle around 350 BC. His analysis of the various forms of arguments marked the beginning of logic as a subject for study in its own right. In particular, Aristotle looked at a type of argument known as a syllogism, consisting of three propositions. The first two propositions, called the premises, logically entail the third proposition, the conclusion. Aristotle's ideas about logic were unrivaled and unchallenged in Western thought for more than 2,000 years. Aristotle approached logic as a branch of philosophy, but in the 1800s, scholars began to study logic as a mathematical discipline. This involved moving from arguments expressed in words to a symbolic logic where arguments could be expressed using abstract symbols. One of the pioneers of this shift to mathematical logic was British mathematician George Boole, who sought to apply methods from the emerging field of symbolic algebra to logic. Algebraic logic. Boole's investigations into logic began in an unconventional way. In 1847, a friend, British logician Augustus de Morgan, became involved in a dispute with a philosopher about who deserved the credit for a particular idea. Boole was not directly involved, but the event spurred him to set down his ideas concerning how logic could be formalized with mathematics, in his 1847 essay Mathematical Analysis of Logic. Boole wanted to discover a way to frame logical arguments so that they could be manipulated and solved mathematically. In order to achieve this, he developed a type of linguistic algebra, in which the operations of ordinary algebra, such as addition and multiplication, were replaced by the connectors that were used in logic. As in algebra, Boole's use of symbols and connectives allowed for the simplification of logical expressions. The three key operations of Boole's algebra were and, or, and not. Boole believed these were the only operations necessary to perform comparisons of sets, as well as basic mathematical functions. For example, in logic, two statements may be connected by and, as in, this animal is covered in hair, and this animal feeds its young with milk, or by or, as in, this animal can swim, or this animal has feathers. The statement, A and B, is true when A and B are both individually true, whereas the statement, A or B, is true if one or both of A and B is true. In Boolean terms, such statements can be given as, for example, equals, not equals A, or even not equals and. Boole's binaries. In 1854, Boole published his most important work, an investigation into the laws of thought. Boole had studied the algebraic properties of numbers and realized that the set, together with operations such as addition and multiplication, could be used to form a consistent algebraic language. Boole proposed that logical propositions could have only two values, true or false, and could not be anything in between. In Boole's logical algebra, truth and falsity were reduced to binary values, 1 for true and 0 for false. Starting out with an initial statement that was either true or false, Boole could then construct further statements and use the and, or, and not operations in order to determine whether or not these further statements were true. Boolean algebra makes it possible to prove logical statements by performing algebraic calculations. Ian Stewart, British mathematician. 1 plus 1 is 1. Despite the resemblance, Boole's true and false binary of 1 and 0 is not the same as binary numbers. Boolean numbers are entirely different from the mathematics of real numbers. The laws of Boole's algebra allow statements that would not be permitted by other forms of algebra. In Boole's algebra, there are only two possible values for any quantity, either 1 or 0. There is also no such thing as subtraction in Boole's algebra. For example, if statement A, my dog is hairy, is true, it has a value of 1, and if statement B, my dog is brown, is true, it also has a value of 1. A and B can be combined to make the statement, my dog is hairy or my dog is brown, which is also true, and also has a value of 1. In Boolean algebra, or behaves like plus and n behaves like. The furthest thing from my mind has been those efforts which try to establish an artificial similarity. Gottlieb Frege. Visualizing results. One way of visualizing Boole's algebra is in the form of diagrams invented by British logician John Venn. In his work Symbolic Logic, Venn developed Boole's theories, employing what became known as Venn diagrams. These depict relations of inclusion and exclusion between sets. They consist of intersecting circles, each one representing a distinct set. A two-circle Venn diagram represents propositions such as all A are B, while a three-circle diagram represents propositions involving three sets. The results of a statement in Boolean algebra can also be assessed using a truth table, in which all possible input combinations are tried and written out. These truth tables were first used by American logician Charles Saunders Peirce in 1893, nearly 30 years after Boole's death. For example, the statement A and B can only be considered true if both A and B are true. If one or both of A and B are false, then A and B is false. Therefore, out of the four possible combinations of A and B, only one results in a true answer. On the other hand, for A or B, there are three possible combinations in which that statement is true, as it will only be false if both A and B are false. More complex statements can also be assessed by drawing truth tables. For example, A and is true when A and B are both true and C is false, and is false when A is false and both B and C are true. Out of 8 possible combinations of true and false, there are 3 in which the statement is true and 5 in which it is false. These Venn diagrams represent 3 of the most basic functions in Boolean algebra, the functions for and, or, and not. The three-circle diagram represents a combination of two functions, or z. Limitations. One drawback in Boole's system of algebra was that it contained no method of quantification. There was no simple way of expressing a statement such as, for all x, for example. The first symbolic logic with quantification was produced in 1879 by German logician Gottlob Frege, who objected to Boole's attempts to turn logic into algebra. Frege's work was followed by Charles Sanders Peirce and another German logician, Ernst Schroeder, who introduced quantification into Boole's algebra and produced substantial works using Boole's system. This logic module is used for teaching how logic gates function in electronic circuits. The gates can be connected to lights or buzzers which go on and off depending on the output. Boole's legacy. It was not until some 70 years after Boole's death that the potential of his ideas was fully grasped. American engineer Claude Shannon used Boole's mathematical analysis of logic to establish the basis of modern digital computer circuits. While working on the electrical circuitry for one of the world's first computers, Shannon realized that Boole's two-value binary system could be the basis of logic gates in the circuitry. Aged just 21, Shannon published the ideas that would form the basis of future computer design in a symbolic analysis of relay and switching circuits, published in 1937. The building blocks of codes now used to program computer software are based on the logic formulated by Boole. Boolean logic is also at the heart of how Internet search engines work. In the early days of the Internet, the AND, OR, and NOT commands were commonly used to filter results to find the specific thing being searched for, but advances in technology allow people today to search using more natural language. The Boolean commands have simply become silent. A search for George Boole, for example, has an implied and between the two words, so that only web pages containing both names will appear in the results. Logic gates, which are physical electronic devices implementing Boolean functions, form an important part of computer circuitry. This table shows the various symbols for each type of logic gate. Truth tables show the possible outcomes of various inputs into the gate. George Boole. Born in Lincoln in 1815, George Boole was the son of a shoemaker who passed his love of science and mathematics on to him. When his father's business collapsed, the 16-year-old George took up a post as an assistant schoolmaster to support his family. He began to study mathematics seriously, starting by reading a book on calculus. He later published work in the Cambridge Mathematical Journal, but still could not afford to study for a degree. In 1849, as a result of his correspondence with Augustus de Morgan, Boole was appointed professor of mathematics at the New Queen's College in Cork, Ireland, where he remained until his premature death at the age of 49. Key works: 1847 Mathematical Analysis of Logic, 1854 An Investigation into the Laws of Thought, 1859 Treatise on Differential Equations, 1860 Treatise on the Calculus of Finite Differences. See also, Syllogistic Logic, Binary Numbers, the Algebraic Resolution of Equations, Venn Diagrams, the Turing Machine, Information Theory, Fuzzy Logic. In context. Key figure: August Mobius field. Applied geometry before 3rd century CE. A Roman mosaic of Ion, Greek god of eternal time, features a zodiac shaped like a Mobius strip. 1847 Johann Listing publishes Vorstudien zur Topologie. After 1882 Felix Klein describes the Kleinsch flash, a shape composed of two Mobius strips. 1957 In the US, the B.F. Goodrich Company produces a patent for a conveyor belt based on the Mobius strip. 2015 Mobius strips are used in laser beam research, with potential application in nanotechnology. A Mobius strip can be made from a simple length of paper. It can be colored in with a crayon in one continuous movement without taking the crayon away from the paper. The shape has a single surface. This can be tested by following the surface of the shape with the eye. Named after 19th-century German mathematician August Mobius, A Mobius strip can be created in seconds by twisting a strip of paper through 180 degrees, then joining its two ends together. The shape that results has some unexpected properties, which have advanced our understanding of complex geometrical figures, a branch of study called topology. The 19th century was a creative period for mathematics, and the exciting new field of topology spawned many new geometrical shapes. Much of this impetus came from German mathematicians, including Mobius and Johann Listing. In 1858, the two men independently investigated the twisted strip, which Listing is said to have discovered first. Once formed, the Mobius strip has only one surface. An ant crawling along that surface would be able to cover both sides of the paper in one continuous movement without crossing the edge of the paper. In geometry, it is considered a classic example of a non-orientable surface. This means that when you trace your finger around the complete strip, the left and right sides of the paper are reversed. The Mobius strip is the simplest non-orientable, two-dimensional surface that can be created in three-dimensional space. Experimenting with the Mobius strip produces other unexpected results. For instance, if you draw a line around the center of the strip and then cut along it, the shape does not divide in half. Rather, it produces a longer, continuous twisted loop. Alternatively, draw a line about a third of the way across the width of the strip, then turn the scissors 90 degrees and cut along its length. The result is one twisted loop linked to a second, thinner twisted loop that is twice as long. A Roman mosaic dating from c. 200 C includes what may be the earliest representation of a Mobius strip, which is thought to represent the eternal nature of time, space, industry, and art. The Mobius strip shape sometimes occurs naturally, such as in the movement of magnetically charged particles within the Van Allen radiation belts that surround Earth and in the molecular structure of some proteins. Its properties have been put to use in everyday applications too. In the early 20th century, the Mobius strip shape was used in continuous loop recording tapes to provide double the playback time. There are also Mobius strip roller coasters, such as the Grand National at Blackpool Pleasure Beach in northern England. The Mobius strip's form has inspired artists and architects. Dutch artist M. C. Escher created a notable woodcut of ants endlessly patrolling the shape. Impressive Mobius strip buildings are being constructed to minimize the impact of the sun's rays. The shape is used in the universal symbol for recycling and also suggested in the mathematical symbol for infinity, echoing the eternity image in the ancient Roman mosaic. Our lives are Mobius strips, misery and wonder simultaneously. Our destinies are infinite, and infinitely recurring. Joyce Carol Oates, American novelist. August Mobius. Born near Naumburg in Saxony, Germany, in 1790, August Ferdinand Mobius was the son of a dance teacher. At the age of 18, he entered the University of Leipzig to study mathematics, physics, and astronomy, and later studied in Göttingen under the great German mathematician Carl Friedrich Gauss. In 1816, Mobius was appointed professor of astronomy at Leipzig and stayed there for the rest of his life, writing treatises on Halley's Comet and other aspects of astronomy. Mobius is associated with a number of mathematical concepts, including Mobius transformations, the Mobius function, the Mobius plane, and the Mobius inversion formula. He also conjectured a geometrical projection known as a Mobius net. Mobius died in Leipzig in 1868. Key works: 1827 The Calculus of Centers of Gravity, 1837 Textbook of Statics, 1843 The Elements of Celestial Mechanics. See also, Graph Theory, Topology, Minkowski Space Fractals. In context. Key figure: Bernhard Riemann Field Number Theory before 1748 Leonhard Euler defines the Euler product, linking a version of what will become the zeta function to the sequence of prime numbers. 1848 Russian mathematician Pafnuty Chebyshev presents the first significant study of the prime counting function pi, after 1901 Swedish mathematician Helge von Koch proves that the best possible version of the prime counting function relies on the Riemann hypothesis. 2004 Distributed computing is used to prove that the first 10 trillion, non-trivial zeros, lie on the critical line. In 1900, David Hilbert listed 23 outstanding mathematical problems. One of them was the Riemann hypothesis, which is still agreed to be one of the most important unsolved problems in mathematics. It concerns the prime numbers, numbers that are only divisible by themselves or 1. Proving the Riemann hypothesis would solve many other theorems. The most noticeable thing about prime numbers is that the larger they are, the more widely spread out they get. Of the numbers between 1 and 100, 25 are prime. Between 1 and 100,000, 9,592 are prime. These values are expressed through the prime counting function, pi, but pi here is not related to the mathematical constant pi. Inputting n into pi gives the number of primes between 1 and n. For example, the number of primes up to 100 gives pi equals 25. Finding the pattern. For centuries, mathematicians' fascination with primes has led them to seek a formula that would predict the values of this function. Aged just 14, Carl Gauss found a rough answer, and he was soon able to find an improved version of the prime counting function that could predict the number of primes between 1 and 1 million as 78,628, which is accurate to 0.2%. The failure of the Riemann hypothesis would create havoc in the distribution of prime numbers. Enrico Bombari, Italian mathematician. A new formula. In 1859, Bernhard Riemann constructed a new formula for pi, which would give the most accurate estimates possible. One of the inputs needed for this formula is a series of complex numbers defined by what is now called the Riemann zeta function, zeta. The numbers that are needed to confirm Riemann's formula for pi are those complex numbers for which zeta equals 0. Some of these, the trivial zeros, are easy to find. They are all the negative, even integers. Finding the others equals 0 is more difficult. Riemann only calculated 3. He believed that non-trivial zeros have one thing in common. When they are plotted on the complex plane, they all lie on the critical line, where the real part of the number is 0.5. This belief is called the Riemann hypothesis. The uranium atom is one example of a heavy atom whose nucleus follows the same statistical behavior as prime numbers, making it extremely difficult to predict. A solution. In 2018, British mathematician Michael Atiyah, then aged 89, said he had found a simple proof for the Riemann hypothesis. He died a few months later, the proof unverified. Although proving the Riemann hypothesis would validate the zeta function's status as the best predictor of the distribution of primes, it still would not allow prime numbers to be fully predicted. Their distribution is to some extent chaotic. But the hypothesis does pin down the blend of predictability and randomness the primes obey. This blend is exactly that exhibited by the energy levels of the nuclei of heavy atoms, according to quantum theory. This profound connection means the hypothesis may one day be proved not by a mathematician, but by a physicist. Bernhard Riemann. The son of a pastor, Bernhard Riemann was born in Germany in 1826. Initially fascinated by theology, he was persuaded to change his degree to mathematics by Carl Gauss, under whom he then studied at the University of Göttingen. The result was a series of breakthroughs that remain influential today. In addition to his work on primes, Riemann helped to formulate the rules for applying calculus to complex functions. His revolutionary understanding of space was used by Einstein in developing relativity theory. Despite his success, Riemann struggled financially. He could finally afford to marry when he was awarded a full professorship by Göttingen in 1862. Just a month later, he fell ill and his health deteriorated until he died of tuberculosis in 1866. Key work. 1868 Über die Hypothesen, Welche der Geometrie zu Grand Liegen. See also, Mersenne primes imaginary and complex numbers, the complex plane, the prime number theorem. In context. Key figure. George Cantor field number theory before 450 BC. Zeno of Elea uses a series of paradoxes to explore the nature of infinity. 1844 French mathematician Joseph Liouville proves that a number can be transcendental, have an infinite number of digits arranged with no repeating pattern and without an algebraic root. After 1901 Bertrand Russell's Barber paradox exposes the weakness of set theory's ability to define numbers. 1913 The infinite monkey theorem explains that given infinite time, random input will eventually produce all possible outcomes. Infinity was a concept that mathematicians had long instinctively mistrusted. It was only in the late 1800s that George Cantor was able to explain it with mathematical rigor. He found there was more than one kind of infinity, an infinite variety, in fact, and that some were larger than others. In order to describe these differing infinities, he introduced transfinite numbers. While he was studying set theory, Cantor aimed to create definitions for every number to infinity. This need arose from the discovery of transcendental numbers, such as pi and e, which are irrational, infinitely long, and are not themselves an algebraic root. Between every algebraic number, including the integers, fractions, and certain irrational numbers, such as there is an infinite number of transcendentals. Counting infinities. To help identify where a number is located, Cantor drew a distinction between two kinds of numbers, cardinals, which are the counting numbers 1, 2, 3, that denote the size of a set, and ordinals such as first, second, or third, which list order. Cantor created a new transfinite cardinal number, Aleph, the first letter of the Hebrew alphabet, to denote a set containing an infinite number of elements. The set of integers that includes the natural numbers, negative integers, and 0, was given the cardinality of the smallest transfinite cardinal, as these are theoretically countable numbers but are actually impossible to count completely. A set with a cardinality of starts with the first item, and ends with the omega item, a transfinite ordinal number. The number of items in a set with a cardinality of is omega. Adding to that set makes a new set of omega plus 1. A set of all countable ordinals, such as omega plus 1, omega plus 1 plus 2, omega plus 1 plus 2 plus 3, will contain omega items. This set cannot be counted, making this infinity larger than countable ones, so it is said to have a cardinality of 1. The set of all sets contains omega items, with a cardinality of. In this way, Cantor's set theory creates infinities nestled inside each, expanding forever. These concentric rings show the different types of numbers, which correspond to different types of infinities. Each ring describes a set of numbers. For example, the set of natural numbers is a small subset of rational numbers, which in turn combine with the set of irrational numbers to make the full set of real numbers. George Cantor. Born in St. Petersburg, Russia, in 1845, George Cantor moved with his family to Germany in 1856. An outstanding scholar, he studied in Berlin and Göttingen. He was later made a professor of mathematics at the University of Halle. Although much admired by today's mathematicians, Cantor was something of a pariah among his contemporaries. His theory of transfinite numbers clashed with traditional mathematical beliefs, and the criticisms of leading mathematicians damaged his career. His work was also criticized by the clergy, but Cantor, who was deeply religious, saw his research as a glorification of God. Overwhelmed by depression, Cantor was institutionalized for much of his later life. He began to receive plaudits in the early 1900s, but lived out his old age in poverty. He died of a heart attack in 1918. Key work. 1915 Contributions to the founding of the theory of transfinite numbers. See also, irrational numbers, Zeno's paradoxes of motion, negative numbers, imaginary and complex numbers, calculus, the logic of mathematics, the infinite monkey theorem. In context. Key figure. John Van Field. Statistics before. Circa 1290, Catalan mystic Ramon Llull devises classification systems using devices such as trees, ladders, and wheels. Circa 1690, Gottfried Leibniz creates classification circles. 1762, Leonhard Euler describes the use of logic circles, now known as Euler circles. After 1963, American mathematician David W. Henderson outlines the connection between symmetrical Venn diagrams and prime numbers. 2003, in the U.S., Gerald Griggs, Charles Killian, and Carla Savage show that symmetrical Venn diagrams exist for all primes. In 1880, British mathematician John Venn introduced the idea of the Venn diagram in his paper on the diagrammatic and mechanical representation of propositions and reasonings. The Venn diagram is a way of grouping things in overlapping circles to show the relationship between them. Overlapping circles. The Venn diagram considers 2 or 3 different sets or groups of things with something in common, such as all living things, or all planets of the solar system. Each set is given its own circle and the circles are overlapped. Objects in each set are then arranged in the circles so that objects that belong in more than one set are placed where the circles overlap. 2 circle Venn diagrams can represent categorical propositions such as all A are B, no A are B, some A are B, and some A are not B. 3 circle diagrams can also represent syllogisms, in which there are 2 categorical premises and a categorical conclusion. For example, all French people are European. Some French people eat cheese. Therefore, some Europeans eat cheese. As well as being a widely used tool for sorting data in everyday life, in contexts ranging from school classrooms to boardrooms, Venn diagrams are an integral part of set theory, due to their distinctive ability to express relationships. Great ideas are the ones that lie in the intersection of the Venn diagram of is a good idea and looks like a bad idea. Sam Altman, American entrepreneur. See also, syllogistic logic, probability calculus, Euler's number, the logic of mathematics. In context. Key figure. Edward Lucas, field number theory before. 1876, Edward Lucas proves that the Mersenne number 2127/1 is prime. This is still the largest prime ever found without using a computer. After 1894, Lucas's work on recreational mathematics is posthumously published in 4 volumes. 1959, American writer Eric Frank Russell publishes Now and Hail, a short story about an alien allowed to play a version of the Tower of Hanoi before his execution. 1966, in an episode of the BBC's Doctor Who, the villain, the celestial toymaker, forces the Doctor to play a 10-disc version of the game. French mathematician Edouard Lucas is believed to have invented his Tower of Hanoi game in 1883. The aim of the puzzle is simple. The challenger is presented with 3 poles, one of which holds 3 discs in order of size, with the largest disc on the bottom. The 3 discs must be moved 1 disc at a time so as to recreate the starting arrangement on a different pole using the smallest possible number of moves, with the restriction that players can only place a disc on top of a larger disc, or onto an empty pole. Solving the puzzle. With just 3 discs, the Tower of Hanoi can be solved in just 7 moves. With any number of discs, the formula 2-1 will give the minimum number of moves. One solution to the challenge employs binary numbers. Each disc is represented by a binary digit, or bit. A value of 0 indicates that a disc is on the starting pole. 1 shows that it is on the final pole. The sequence of bits changes at each move. According to legend, if monks at a certain temple in either India or Vietnam succeed in moving 64 discs from one pole to another in line with the rules, the world will end. However, even using the best strategy and moving 1 disc per second, it would take 585 billion years to complete the game. A form of the Tower of Hanoi is a popular toy for small children. Versions with 8 discs are often used to test developmental skills of older children. See also, wheat on a chessboard. Mersenne primes binary numbers. In context. Key figure. Henri Poincaré field geometry before. 1736 Leonhard Euler solves the historical topological problem of the 7 bridges of Königsberg. 1847 Johann Listing coins the term topology as a mathematical subject. After 1925 Russian mathematician Pavel Alexandrov establishes the basis for studying the essential properties of topological spaces. 2006 Grigory Perelman's proof of the Poincaré conjecture is confirmed. Topology is, in simple terms, the study of shapes without measurements. In classical geometry, if a pair of shapes has equal corresponding lengths and angles, and you can slide, reflect, or rotate one of the shapes into the other, they are congruent, a mathematical way of saying they are identical. To a topologist, however, 2 shapes are identical, or invariant, in topological terminology, if they can be molded one into the other by continuous stretching, twisting, or bending, but with no cutting, piercing, or sticking together. This has led to topology being called rubber sheet geometry. For more than 2,000 years, from the time of Euclid, c. 300 BC, geometry was concerned with classifying shapes by their lengths and angles. In the 18th and early 19th centuries, some mathematicians began to look at geometric objects differently, considering the global properties of shapes beyond the confines of lines and angles. Out of this grew the mathematical field of topology, which by the early 1900s had moved far from the notion of shape to embrace abstract algebraic structures. The most ambitious and influential exponent of this was French mathematician Henri Poincaré, who used complex topology to throw new light on the shape of the universe itself. Birth of a new geometry. In 1750, Leonhard Euler revealed that he had been working on a formula for polyhedra, 3-dimensional figures with 4 or more planes, such as a cube or pyramid, that involved their vertices, edges, and faces rather than lines and angles. What he postulated became known as Euler's polyhedral formula, V plus Fe equals 2, where V is the number of vertices, F the number of faces, and E the number of edges. The formula suggested that all polyhedra shared basic characteristics. However, in 1813, another Swiss mathematician, Simon Lullier, noted that Euler's formula was not true for all polyhedra. It was false for polyhedra with holes and for nonconvex polyhedra, shapes with some diagonals not contained within or on the surface. Lullier devised a system whereby every shape had its own Euler characteristic, and shapes with the same Euler characteristic were related regardless of how much they might be manipulated. The term topology, derived from the Greek topos, meaning a place, was introduced to the mathematical world by German mathematician Johann Listing in 1847 in his treatise Vorstudien zur Topologie, although he had used the word in correspondence at least 10 years earlier. In particular, Listing was interested in shapes that did not satisfy Euler's formula or defied the conventions of having distinct, outside, and inside, surfaces. He even devised a version of the Mobius strip, a surface that has only one side and one edge, a few months before August Mobius. Around the same period, another German mathematician, Bernhard Riemann, devised new geometrical coordinate systems that extended beyond the limits of the 2D and 3D systems devised by René Descartes. Riemann's new framework enabled mathematicians to explore shapes in 4 dimensions or higher, including seemingly impossible shapes. One such shape was the Klein bottle, devised in 1882 by German mathematician Felix Klein. He imagined joining 2 Mobius strips together to create a shape that has only one surface, is non-orientable, and unlike a Mobius strip, has no edge or boundary curve. As it has no intersections, the shape can only truly exist in 4-dimensional space. If the shape is represented in 3D, it has to intersect itself, which is where it starts to look like a bottle. Topologists applied the term two-manifold to shapes such as the Mobius strip and Klein bottle to describe their surfaces, which are 2-dimensional surfaces embedded within a space of higher dimension. Euler's formula, V plus Fe equals 2, works for most polyhedra, including a cube. Its values of V equals 8, F equals 6, and E equals 12, when fed into the formula, produce the calculation 8 plus 6 to 12, which equals 2. Algebraic topology allows us to read qualitative forms and their transformations. Stephanie Strickland, American poet. To a topologist, a coffee mug is identical in shape to a donut, because by pulling, stretching, and bending one, you could mold one into the shape of the other. A universal conjecture. The shape of the universe has long been a source of speculation. We appear to inhabit a 3D world, but to make any sense of its shape we need to take ourselves outside this, into 4 dimensions. In the same way, to gain a sense of the shape of a 2D surface, we need to look down on it in 3 dimensions. A starting point would be to imagine that we inhabit a universe that is a 3D surface embedded within 4 dimensions. Taking this one step further, you could consider that this 3D surface is actually a sphere embedded in a 4D space, also known as a 3-sphere. A 2-sphere is equivalent to a normal sphere in a 3D space. In 1904, Henri Poincaré went even further, producing a theory that would help to lay a topological basis for understanding the shape of the universe. He proposed what became known as the Poincaré conjecture. Every simply connected, closed 3-manifold is homeomorphic to the 3-sphere. A 3-manifold is a shape that appears 3D when its surface is enlarged but exists within higher dimensions, and simply connected means that it has no holes, like an orange but not a donut. A closed shape is finite, with no boundaries, like a sphere. Finally, homeomorphic describes shapes that can be molded into each other, such as a mug and a donut. A donut and an orange, however, are not homeomorphic because of the hole in the donut. According to Poincaré, if it could be shown that the universe did not contain holes, then you could model it as a 3-sphere. To establish whether it contained holes, you could, in theory, conduct an experiment with string. Imagine you are an explorer traveling around the universe from a set point, and unraveling a ball of string as you go. When you get back to your starting point, you see the end of the string that you started with. You take both ends, and start to gather in the string, pulling both ends. If the universe is simply connected, then you would be able to gather in the whole string, like a loop following the smooth contours of a sphere. If you had passed through holes or gaps, then the string could get snagged. For example, if the universe were shaped like a donut, and in your travels you wrapped your string around its girth, the string would get caught. You would not be able to gather in the string without pulling it beyond the universe. The Black Dog Trademark robot is designed to carry loads over rough terrain. The robot's moves are computed using algebraic topology that can predict and model the surrounding space. Shaping the future. Topology developments still continued during the 1900s. In 1905, French mathematician Maurice Fréchet devised the idea of a metric space, a set of points along with a metric that defines the distance between them. Also at the turn of the 20th century, German mathematician David Hilbert invented the idea of a space that took the Euclidean spaces of 2 and 3 dimensions and generalized them to infinite dimensions. Mathematics could then be done in any dimension in much the same way as in a 3D coordinate system. This area of topological mathematics has become known as infinite-dimensional topology. The field of topology is now vast, embracing abstract algebraic structures far removed from a simple notion of shape. It has wide-ranging applications in areas such as genetics and molecular biology, such as helping to unravel the knots created around DNA by certain enzymes. Probably no branch of mathematics has experienced a more surprising growth. Raymond Lewis Wilder, American mathematician. Henri Poincaré. Born in 1854 in Nancy, France, Henri Poincaré showed such early promise that he was described by a teacher as a monster of mathematics. He graduated in the subject from the Paris École Polytechnique and earned his doctorate from the University of Paris. In 1886, he was appointed as chair of mathematical physics and probability at the Sorbonne in Paris, where he spent the rest of his career. In 1887, Poincaré won a prize from King Oscar II of Sweden for his partial solution of the many variables involved in determining the stable orbit of 3 planets around one another. A self-confessed mistake threw his calculations for the stable orbit into doubt, but in turn paved the way for the study of chaos theory. He died in 1912. Key works: 1892-99 Les méthodes nouvelles de la mécanique céleste. 1895 Analysis Sidus. 1903 La science et l'hypothèse. See also Euclid's Elements Coordinates, the Mobius strip Minkowski space proving the Poincaré conjecture. In context. Key figure: Jacques Hadamard field number theory before. 1798 French mathematician Adrien-Marie Legendre offers an approximate formula to determine how many prime numbers there are below or equal to a given value. 1859 Bernhard Riemann outlines a possible proof for the prime number theorem, but the necessary mathematics to complete it does not yet exist. After 1903 German mathematician Edmund Landau simplifies Hadamard's proof of the prime number theorem. 1949 Paul Erdos in Hungary and Adel Selberg in Norway both find a proof of the theorem using only number theory. The prime numbers, those positive whole numbers that have only 2 factors, themselves and 1, have long fascinated mathematicians. If the first step was to find them, and they are frequent among the small numbers, the next step was to identify a pattern to describe their distribution. More than 2,000 years before, Euclid had proved that there are infinitely many primes, but it was only at the end of the 1700s that Legendre stated his conjecture, a formula to describe the distribution of primes. This became known as the prime number theorem. In 1896, Jacques Hadamard in France and Charles-Jean de la Vallée-Poussin in Belgium both proved the theorem, quite independently. It is evident that primes decrease in frequency as numbers get larger. Of the first 20 positive whole numbers, 8 are prime, 2, 3, 5, 7, 11, 13, 17, and 19. Between the numbers 1000 and 1020, there are only 3 prime numbers, and between 1 million and 1,020,020, the only prime is 1,000,003. This seems reasonable. The higher the number, the more numbers that could be divisors exist below it. Many notable mathematicians have puzzled over how primes are distributed. In 1859, German mathematician Bernhard Riemann worked toward a proof in his paper on the number of primes less than a given magnitude. He believed that complex analysis, a branch of mathematics in which ideas of function are applied to complex numbers, combinations of real numbers, such as 1, and imaginary numbers such as would lead to a resolution. He was right. The study of complex analysis developed, fueling the proofs of Hadamard and Poussin. What the theorem says? The prime number theorem is designed to calculate how many primes there are less than or equal to a real number x. It states that pi is approximately equal to x divided by ln as x gets larger and tends to infinity. Here pi denotes the prime counting function and is unrelated to the number pi, and ln is the natural logarithm of x. To explain the theorem slightly differently, for a large number x, the average gap between primes from 1 to x is approximately ln. Or, for any number between 1 and x, the probability of it being a prime is approximately 1 divided by ln. The prime numbers are the building blocks for numbers in mathematics, just as the elements are for compounds in chemistry. Fundamental to understanding this is the Riemann hypothesis, an unsolved conjecture, which, if true, could reveal a huge amount more about prime numbers. Primes tend to decrease in frequency as numbers get larger. Although there are 2 primes between 30 and 40, and 3 between 40 and 50, the accuracy of the prime number theorem increases at higher numbers. The prime numbers grow like weeds among the natural numbers, seeming to obey no other law than that of chance. Don Zagier, American mathematician. Jacques Hadamard. Born in Versailles, France, in 1865, Jacques Salomon Hadamard became interested in mathematics thanks to an inspiring teacher. He obtained his doctorate in Paris in 1892, and the same year won the Grand Prix des Sciences Mathématiques for his work on primes. He moved to Bordeaux to lecture at the university, and there proved the prime number theorem. In 1894, Alfred Dreyfus, a Jewish relative of Hadamard's wife, was falsely accused of selling state secrets, and was sentenced to life in prison. Hadamard, who was also Jewish, worked tirelessly on behalf of Dreyfus, and he was eventually freed. Hadamard's brilliant career was marred by personal loss. 2 of his sons died in World War I, and another in World War II. The death of his grandson Etienne in 1962 was a final blow. Hadamard died a year later. Key works: 1892 Determination of the number of primes less than a given number. 1910 Lesson on the calculus of variations. See also Euclid's Elements, Mersenne primes, imaginary and complex numbers, the Riemann hypothesis. Introduction. In 1900, as the arms race that led to World War I intensified, German mathematician David Hilbert attempted to anticipate the directions that mathematics would take in the 20th century. His list of the 23 unsolved problems he considered crucial was influential in identifying the fields of mathematics that could be fruitfully explored by mathematicians. New century, new fields. One area of exploration was the foundations of mathematics. In seeking to establish the logical basis of mathematics, Bertrand Russell described a paradox that highlighted a contradiction in George Cantor's naive set theory, leading to a reappraisal of the subject. These ideas were taken up by André Weil and others, using the pseudonym Nicolas Bourbaki. Starting from the basics, they met in the 1930s and 40s, rigorously formalizing all branches of mathematics in terms of set theory. Others, notably Henri Poincaré, explored the newly established field of topology, the offshoot of geometry dealing with surfaces and space. His famous conjecture concerns the two-dimensional surface of a three-dimensional sphere. Unlike many of his peers in the 1900s, Poincaré did not confine himself to any one single field of mathematics. As well as pure mathematics, he made significant discoveries in theoretical physics, including his proposed principle of relativity. Similarly, Hermann Minkowski, whose primary interest was in geometry and the geometrical method applied to problems in number theory, explored the notion of multiple dimensions, and suggested spacetime as a possible fourth dimension. Emmy Noether, one of the first female mathematicians of the modern era to gain recognition, came to the field of theoretical physics from a perspective of abstract algebra. The computer age. In the first half of the 1900s, applied mathematics was largely concerned with theoretical physics, especially the implications of Einstein's theories of relativity, but the latter part of the century was increasingly dominated by advances in computer sciences. Interest in computing had begun in the 1930s, in the search for a solution to Hilbert's Entscheidungsproblem and the possibility of an algorithm to determine the truth or falsity of a statement. One of the first to tackle the problem was Alan Turing, who went on to develop code-cracking machines during World War II that were the forerunners of modern computers. He later proposed the test of artificial intelligence. With the advent of electronic computers, mathematics was in demand to provide methods of designing and programming computer systems. But computers also provided a powerful tool for mathematicians. Hitherto unsolved mathematical problems such as the four-color theorem often involved lengthy calculations, which could now be done quickly and accurately by computer. Although Poincaré had laid the foundations of chaos theory, Edward Lorenz was able to establish the principles more firmly with the aid of computer models. His visual images of attractors and oscillators, along with Benoit Mandelbrot's fractals, became icons of these new fields of study. With the advent of computers, the secure transfer of data became an issue, and mathematicians devised complex cryptosystems using the factorization of large prime numbers. Launched in 1989, the World Wide Web facilitated the rapid transmission of knowledge, and computers became a part of everyday life, especially in the field of information technology. New logic, new millennium. For a while, it seemed electronic computing could potentially provide answers to almost all problems. But computing science was based on a binary system of logic first proposed by George Boole in the 1800s, and the polar opposites of on-off, true-false, 0 to 1, and so on could not describe how things are in the real world. To overcome this, Lotfizadeh suggested a system of fuzzy logic, in which statements can be partly true or false, in a range between 0 and 1. In 2000, 21st-century mathematics was heralded in a similar spirit to that of the 20th century, when the Clay Mathematics Institute announced 7 Millennium Prize problems, offering a $1 million prize for any of their solutions. As yet, only the Poincare conjecture has been solved. Grigori Perelman's proof was confirmed in 2006. In context. Key figure. David Hilbert Field's logic, geometry before. 1859 Bernhard Riemann proposes the Riemann hypothesis, a famous problem that will later be number 8 on Hilbert's list and remains unresolved today. 1878 George Cantor advances the continuum hypothesis, later number 1 on Hilbert's list. After 2000 the Clay Institute issues a list of 7 Millennium Prize mathematical problems, offering $1 million for each problem solved. 2008 in a bid to stimulate major new mathematical breakthroughs, the U.S. Defense Advanced Research Projects Agency announces its list of 23 unsolved problems. It requires a special technical brilliance and self-confidence to predict relevant problems for the next 100 years, but this is what German mathematician David Hilbert did in 1900. Hilbert possessed a substantial grasp of most fields of mathematics. At the International Mathematical Congress in Paris in 1900, he confidently announced his choice of 23 questions that he believed should occupy mathematicians' thoughts in the decades to come. This proved prescient. The math world rose to the challenge. The range of problems. Many of Hilbert's questions are highly technical, but some are more accessible. Number 3, for instance, asks if one of any two polyhedra of the same volume can always be cut into finitely many bits that can be reassembled to create the other polyhedron. This was soon resolved in 1900 by German-born American mathematician Max Dehn, who concluded that it could not. The continuum hypothesis, the first problem on Hilbert's list, pointed out that the set of natural numbers was infinite, but so was the set of real numbers between 0 and 1. As a result of the work of German mathematician George Cantor, it was agreed that the first infinity was smaller than the second. The continuum hypothesis also stated that there was no infinity lying between these two infinities. Cantor himself was sure this was true, but he could not prove it. In 1940, Austrian-American logician Kurt Gödel showed it could not be proved that such an infinity exists. And in 1963, American mathematician Paul Cohen showed it could not be proved that such an infinity does not exist. Hilbert's first problem is substantially resolved, although set theory is a complex subject, and much more work on it remains to be done. Of Hilbert's 23 problems, 10 are considered resolved, 7 have been partially solved, 2 have been classed as too vague to ever be definitively solved, 3 remain unsolved, and 1 is really a physics problem. Among the unsolved problems is the Riemann hypothesis, which some observers think will remain unsolved for the foreseeable future. The infinite. No other question has ever moved so profoundly the spirit of man. David Hilbert. Challenges for the future. Hilbert's remarkable achievement was to accurately predict what would concern mathematicians in the 1900s and beyond. When American mathematician and Fields Medal winner Steve Smale came up with his own list of 18 questions in 1998, it included Hilbert's 8th and 16th problems. 2 years later, the Riemann hypothesis was also one of the Clay Institute's Millennium Prize problems. Today's mathematicians face further challenges, but aspects of Hilbert's problems, especially those that are still unsolved, remain relevant.
Problem solving and theory building go hand in hand. That's why Hilbert risked offering a list of unsolved problems instead of presenting new methods or results. Rödiger Thiel, German mathematician. David Hilbert. Born in Prussia in 1862 to German parents, David Hilbert entered the University of Königsberg in 1880 and later taught there before becoming professor of mathematics at the University of Göttingen in 1895. In this role, he turned Göttingen into one of the mathematical hubs of the world and taught a number of young mathematicians who later made their own mark. Hilbert was renowned for his broad understanding of many areas of mathematics, and had a keen interest in mathematical physics, too. Exhausted by anemia, he retired in 1930, and Göttingen's math faculty soon declined after the Nazi purges of Jewish colleagues. Despite his great contribution to mathematics, Hilbert's death in 1943, during World War II, went largely unnoticed. Key works: 1897 Commentary on Numbers, 1900 The Problems of Mathematics, 1932, 35 collected works, 1934, 39 Foundations of Mathematics. See also, Diophantine equations, Euler's number, the Goldbach conjecture, the Riemann hypothesis, transfinite numbers. In context. Key figure: Francis Galton, field number theory before 1774. Pierre-Simon Laplace shows the expected pattern of distribution around the norm. 1809 Carl Friedrich Gauss develops the least squares method of finding the best fit line for a scatter of data. 1835 Adolphe Quetelet advocates the use of the bell curve to model social data. After 1900 Karl Pearson proposes the chi-squared test to determine the significance of differences between expected and observed frequencies. Statistics is the branch of mathematics that is concerned with analyzing and interpreting large quantities of data. Its foundations were laid in the late 1800s, principally by British polymaths Francis Galton and Karl Pearson. Statistics investigates whether the pattern of recorded data is significant or random. Its origins lie in the efforts of 18th-century mathematicians such as Pierre-Simon Laplace to identify observational errors in astronomy. In any set of scientific data, most errors are likely to be very small, and only a few are likely to be very large. So when observations are plotted on a graph, they create a bell-shaped curve with a peak created by the most likely result, or norm, in the middle. In 1835, Belgian mathematician Adolphe Quetelet posited that characteristics, such as body mass, within a human population follow a bell curve pattern, in which values around the mean are most frequent. Higher and lower values are less frequent. He devised the Quetelet index to indicate body mass. Typically, plotting two variables, such as height and age, on a graph creates a messy scatter of data points that cannot be linked by a neat line. However, in 1809, German mathematician Carl Friedrich Gauss found an equation to create a best-fit line, which would show the relationship between the variables. Gauss used a method called least squares, which involves adding up the squares of the data. This is still used by statisticians. By the 1840s, mathematicians such as Auguste Brevet were looking at the level of error that could be accepted for this line, and tried to pin down the significance of the midpoint or median of a set of data. Francis Galton invented the quincunx to model the bell curve. His original design had beads dropping over pegs. Correlation and regression. It was first Galton, then Pearson, who began to draw these threads together. Galton was inspired by his cousin Charles Darwin's work on evolution, and his aim was to show how likely it was that factors such as height, physiognomy, and even intelligence and criminal tendencies might be passed from one generation to the next. Galton and Pearson's ideas are tainted by the doctrine of eugenics and racial improvement, but the techniques that they developed have found applications elsewhere. Galton was a rigorous scientist, determined to analyze data to show mathematically how probable outcomes are. In his innovative 1888 book Natural Inheritance, Galton showed how two sets of data can be compared to show if there is a significant relationship between them. His approach involved establishing two related concepts that are now at the heart of statistical analysis: correlation and regression. Correlation measures the degree to which two random variables, such as height and weight, correspond. It often looks for a linear relationship, that is, a relationship that gives a simple line on the graph, with one variable changing in step with the other. Correlation does not imply a causal relationship between the two variables. It simply means they vary together. Regression, on the other hand, looks for the best equation for the graph line for two variables, so that changes in one variable can be predicted from changes to the other. Galton built an anthropometric laboratory to collect information on human characteristics, including head size and quality of vision. It generated huge amounts of data that he had to analyze statistically.